Okay. Okay, so now we are going to talk about how to determine the best split. Okay, so before the break, we looked at various ways in which we could split different features, right? Like, so now the most important question is like, how do I determine which is the best split, right? So let's start with an example. So here I have three different features. Okay, so gender, car type, and customer ID. Okay, and in this example, I have 10 records of class 0 and 10 records of class 1. Okay, so each split divides the examples into two parts or three parts, depending on however number of parts you're splitting, and like, and you see the number of class 0 and class 1. Okay, now which one do you think is the best split here? Yeah, gender. Anything else? Yeah,
I'd say car type.
car type. Okay, so what's your answer? It's car type. So there are a couple of car types and one gender. Any other answers? So why not customer ID? Anyone thinks customer ID is a good way to split? Why not?
I found it. There's no you're not like inducing the relationship between.
Yeah, so with the customer ID, you see that for 20 different records, well, the customer ID is unique, right? Like the customer ID has to be unique. So which means you're really splitting the records into 20 different parts, right? Like, so each has only one example. Now, would it generalize for a new customer? The new customer is going to have a totally new customer ID, right? Like, so this is a really useless. In fact, you should not use customer ID feature in your classification at all, right? Because it's not discriminative. Like, so it is so unique for each customer that you are not going to learn anything from that to make better predictions. So you should not use, if your data set actually has customer ID or any ID for that matter, for example, your metrical, right? You should just ignore that feature for classification because it's not going to be useful for classification, right? So then it comes down to gender and car type. So which is better, gender or car type? Yeah. So now comes the question of which is more discriminative, right? So if I do gender, it's almost 50-50, right? Like, so I'm not making progress in my problem by doing gender, because in the left side you have 6 class 0, 4 class 1. In the right side you have 6 class 1 and 4 class 0, right? So I'm not making much progress in the classification problem. However, when I use car type, you see that with sports car, it's 100% class 0. With family and luxury car, it's majority class 1, right? Like, so it's 1 out of 7, so 1 out of 8 class 0, so it's almost class 1. The other one is 75% class 1, right? So which means this is probably the best. Sorry. So this is probably, well, why is it not writing? Okay. So this is probably the best feature to spread, right? Now, what logic did we use here? Like, so the logic that we use is after the split, I want to see only one class as much as possible. Okay, or in other words, we are looking for splits which results in homogeneous nodes. By homogeneous, I mean like there is just one class, right? Like, or close to being homogeneous, right? Like, so the criteria for splitting is nodes with homogeneous class distribution are preferred. Is that clear? So let's look at some examples. Like, so for example, let's say I have something like this versus something like this, right? So in this case, the second example is more homogeneous, while this is not homogeneous. This is non-homogeneous because it's 50-50. This is more heterogeneous, right? We can also say that this has low degree of impurity. Some split is pure when it is just one class, okay? So the degree of impurity here is just 1 out of 10. Okay, so the low degree of impurity, in this case, this has high degree of impurity. Okay, now there are many ways to measure homogeneity or impurity. Okay, so there are different measures of node impurity. Okay, we are going to look at 3 example measures. Like, so one is called Gini index, or you could just look at the classical entropy. Okay, or you could also look at misclassification error. Is that clear? So we will see the definition of all these 3 measures soon. But before that, let's look at the general principle. The general principle is, before splitting, you have certain number of class 0 and class 1. So you will use your measure to compute the node impurity or homogeneity, whatever you care about. Okay, so that is before splitting. Now there are 2 possible ways to split. Let's say A and B. Each split is going to give you new tables, right? Like new nodes. Each node is going to have some measure of purity, right? I can combine these 2 things together. Like, we'll see how to combine soon. Okay. Now the gain due to split is simply P minus M1 versus P minus M2. So whichever has maximum gain, I'm going to use that as my split. Is that clear? Okay. So now let's look at these measures in detail. So first we are going to look at, I don't know if it is Gini index or Gini index, whatever way you want to pronounce it. So the Gini index is defined as follows. So Gini of T is given by 1 minus summation over J, P of J given T whole square. Okay, so that's the metric. Let's do some examples so that you get a feel of how this looks like, right? Like, so let's take the first example, which is a good split, and we'll do another example. Okay, so the Gini here is given by 1 minus the frequency of each class square. Okay, so it's going to be 1 minus 0 square minus 6 by 6 square. It's going to be 1 minus 0 square minus 1 square, so it's going to be 0. So the Gini index for an ideal split is 0. Okay, now let's do the Gini for this split. So it's going to be 1 minus 1 by 6 square minus 5 by 6 square. Okay, so if you do the calculation, this is 0.278. So what do you think would be the Gini for like a completely heterogeneous node? Like, for example, I have C1 being 3, C2 being 3. So what would be the Gini for this? Yeah. Is it 1? So it's going to be 1 minus half square minus half square. So it's going to be 1 minus It's going to be half, right? So 0.5. So this means that the range of Guinea is between 0 to 0.5. When it is completely homogeneous, it's 0. When it's completely heterogeneous, it's 0.5. Everything is in between. Is that clear? So now let's go back here. For each table, we can compute Guinea, right? So now the question is, how do I merge these two things into a single metric, M1? So the typical way in which we would do that is to basically do Guinea split, which is summation I is equal to 1 to k ni by n times Guinea of I. Okay, so we'll consider we are basically doing weighting each Guinea to come up with the final one. Okay, so here is a worked out example. So in this case, I start with 7 class 1 and 5 class 2. I'm considering some test which splits the data like this. Okay, now the Guinea for N1 is this, the Guinea for N2 is this. So when you do the weighted Guinea, that is this. So before the split, my Guinea index was 0.486. After the split, it became 0.361. So we wanted to go to 0, right? So which means this is a meaningful split. When I do the split, I'm making progress in my prediction problem. So the gain is given by this value. Okay, so this is for one condition B, right? Similarly, you can do it for another condition, another condition, another condition. So check which condition has the maximum gain. Is that clear? Now you can also use this to decide whether you want to do two-way or multi-way. Okay, so for example, in this car type example, right? So there are three possibilities. Either I do multi-way split or I do the two-way splits, right? I can actually compute the Gini for all the three and find what is the best. So for this particular problem, I think this is going to be the best, right? So this has the lowest Gini. So when you do the gain, this is going to have the maximum gain. Is that clear? So completely data-driven way of selecting the tests. Okay, so this you can implement as a program if you want, right? Like so. However, I'm not going to ask you to implement decision trees in your assignment. Like so, you will be directly using scikit-learn's decision tree for your third assignment. Okay, so now what about continuous attributes? Right, like for example, let's take income. Right, a naive way to do this is consider every possible income, do the two-way split, compute the Gini, right? So it's going to be very expensive idea, right? Like so, there's actually a more efficient way to do continuous income, like continuous attribute. Like so, what we do here is we basically sorted all the values that we have in the data set. Okay, now we are going to consider splits that are between two values. So which means if you have 10 values, then there are only 9 possible splits, right? So for each split, you compute the Gini separately. So now this is going to help you to find the ideal split. For example, this particular example, the best split possible is 97K. Like at 97K, Gini is 0.3, so you're going to get maximum gain. Is that clear? Any question? Now this is one way to measure impurity, right? Like so there are other ways. For example, the more classical way to measure impurity is through entropy. Sorry. Entropy of T is given as minus summation over J, P of J given T times log P of J given T. Okay. So let's try to do this for some examples. So I'm doing C1, C2 being, we're going to do the same example. So 0 and 6, C1 and C2 being 1 and 5. Let's also do this for C1 and C2 being 3 and 3. Okay. So what would be the entropy here? It's going to be, so what would be the value of entropy here? Yeah. Well, you can say that even without doing any calculations, like so, there is no variations here. Like it's just one class. So the entropy should be 0. Okay, so it's going to be minus 0 log 0 minus 1 log 1. Okay, whatever value doesn't exist, you assume it is 0, so this becomes 0. So log 0 doesn't exist, but like 0 times log 0 is 0, log 1 is 0. Okay, so what about this? So entropy here is going to be minus 1 by 6 log 1 by 6 minus 5 by 6 log 5 by 6. If you do the calculation, this is 0.65. Okay, now what is the entropy for this case? It's going to be minus 1 by 2 log 1 by 2 minus 1 by 2 log 1 by 2, right? So this becomes minus log 1 by 2, which is log 2, which is 1. So entropy is between 0 to 1. When it is 0, it's completely homogeneous. When it is 1, it is completely heterogeneous. Is that clear? There's also the third metric, which is classification error, but I'm not going to do the examples for that. It's really easy. So classification error is defined as 1 minus max of P of I given T. Okay, I'm not going to do running examples like so. Now, depending on which metric you're using, there are different decision tree algorithms. For example, so Gini is used in algorithms like CART, SLIC, Sprint. Okay, while entropy is used in algorithms like ID3, C4.5. Okay, it really doesn't matter at this point, like that you know what exactly these algorithms are doing. I think there was a period in machine learning research where people were coming up with hundreds or thousands of variations of decision trees. Like each of these algorithm is basically making some different design choices on how to split or what conditions to look at or when to stop, etc. Okay, so for all practical purposes, like you don't need to know these things. Okay, now here is a comparison of all these three different metrics. Okay, so you see that when you're here, it is all class 0. When you're here, it is all class 1. Okay, so in both the ends, the metrics are 0. So the middle point is where you have 50% class 0, 50% class 1. That is when all these metrics peak, and they all peak here, like with, like, for example, Gini and misclassification, maximum value 0.5 and entropy maximum value 1. As you can see, it really doesn't matter which metric you are using. Okay, so they are all similar in trends, right? Like so like you could use either of these metrics, it doesn't matter. Is it clear? Any question? Okay, so there's one problem with directly using these metrics though. Let's go back to our first example. Yeah. If I use, well, it doesn't matter which metric I'm using. Let's just, for example, let's say I'm using entropy. If I use entropy as my metric, which one of these three features will get selected for maximum gain? Yeah. No.
Customer ID.
Customer ID. Customer ID has actually 0 entropy, right? Like so, because once you divide things by customer ID, it's going to be always pure, right? So this is the problem with all these metrics. Like it doesn't matter whether you're using entropy or Gini or misclassification error, they are all going to prefer customer ID while they should ideally prefer car type, right? How can we fix this problem? Yeah. Yeah, so the minimum the split groups are, the better, right? Like so like here, like you're, yes, you can take any data set and split it like as one example per node, then you're going to get 0 entropy, right? Like so you don't want too many splits. In some sense, you want to penalize when there is too many split. That is going to avoid this like issue, right? So how do we do that? Like, so one way to do that is to consider like what is called gain ratio instead of gain. Okay, so gain ratio is defined by gain divided by split info. Okay, so this you're basically like you're not just considering the gain, you're also taking into account the splitting info. Like it's in the denominator, so which means you need to have lower number of splits. Okay, so split info is given by minus summation I is equal to 1 to k ni by n log ni by m. Okay, so this is basically considering whether you are having minimal splits with more items per split, right? Like, so you want lesser number of splits and more examples in each split. Okay, so this is taken care of by this denominator. Is that clear? Any question? Okay, so now let's talk about the final design choice, question 3, which is when to stop splitting. Okay, so I have a splitting algorithm, right? Like, so I know how to come up with tests. I have a metric which picks the best test, right? So in theory, I can just continue this forever until I reach a situation where no more tests are available or no more data points are available, right? Is that a good idea? So can I just run this algorithm until end? What kind of issues you would face if you do that? The classical question here. Yeah, you would start overfitting. So if you are considering every possible test, this basically means you're giving importance to every information that exists in the training set. You're going to significantly overfit. Okay, decision trees overfit easily. Okay, so here is one example, like where as the size of the tree grows, the training accuracy keeps increasing. This is always true. As the size of the tree grows, the training accuracy should always increase. It is going to reach 100% at some point for sure, because it's the non-parametric method, right? Like, so like you can perfectly fit the training set. Okay. However, you see that the test set accuracy has already started reducing from here, which means the model has started to overfit. Okay. Now, how do we avoid overfitting for decision trees? Well, with parametric models, we know ideas, right? Like, so we can actually do L2 regularization, right? Or you could just add more examples, right? But adding more examples is not going to help with decision trees. Like, so you are still you're going to overfit even more with more examples, like as long as you grow the tree to the end, right? So what kind of solutions we can come up with for overfitting? Yeah. You can do model selection on the size of the tree. Yes, you can always do that. Like, so just compute the training and validation set, measure wherever the validation set peaked, use that as your tree, right? Yes, you can do that. Any other idea? Yeah.
Just set sort of like a floor, and when the information gain is lower than this floor, we stop.
You can also set thresholds on information gain, right? So you can say that, oh, whenever the information gain gets lower than this, then we are overfitting to the patterns in the training set, which doesn't exist in the test set. So maybe we should stop, right? Some sort of early stopping, right? So what else can we do? Oh, by the way, there are many ways to stop, and that also differentiates different algorithms. Okay, so let's think about more solutions. Like, what other things you can do? Yeah.
Limit the depth of the tree.
Limit the depth of the tree. Well, that is a different way to do that same thing, right? So you can say that, oh, I don't want my tree to grow more than 10 layers deep. You could do that. That's a hyperparameter. If you do sklearn for decision trees, like you will find tree depth as one of the hyperparameter. There might be threshold, but there's definitely like a min examples, like minimum examples in a node as another way. Like you can say that, oh, whenever the node starts having less than 10 examples, then I don't want to split further because 10 is too small, right? Like then I might overfit, right? Like that is a hyperparameter in scikit-learn. So there are many ways to do this, okay? But I can group all these techniques into two major ways of like avoiding overfitting. One is to stop growing the tree earlier, okay? Like the depth hyperparameter or the minimum example hyperparameter, these are preventing overfitting, right? Like so you say, oh, I don't want to continue further, so you're stopping earlier, right? The second strategy, which is always a good idea, is to allow to overfit and then post prune the tree. Okay, it's always a good idea to let the model overfit, then you prune to whatever level you want to prune. Okay, and there are two main ways to do this pruning. So one is called reduced error pruning. The other is called rule post pruning. Okay, so what is reduced error pruning? So the idea of reduced error pruning is, let's say I have a tree which looks like this. Okay, what tests we have there, it doesn't matter. Just as an example, you could have a really complex tree. Okay, so reduced error pruning just means that you let the tree completely grow, then you start removing nodes bottom up. Okay, so I'll go to the bottommost thing, like for example, I will remove this node and see how it improves the validation performance. Okay, if it doesn't increase my validation error, like even if it stays same or gets better, I'm going to do this removal. Okay, so once I remove this, then I'm going to consider removing this. Then I'm going to consider removing this. I'm going to consider removing this, removing this, removing this, right? So we will remove nodes one after another from bottom up and see if it is helping with validation performance. And we will stop this process when the validation error is increasing. Is that clear? So this is one way to allow the model to overfit and then post prune. Okay. Now, one of the big disadvantage of this method is it's kind of okay when you're in the bottom, right? But when you're in the top, for example, when you remove this node, you're essentially removing the entire subtree, right? So which means there is less flexibility in the removal process when you do reduce error pruning. Okay, so this is what the rule post pruning is going to fix. Okay, but before that, like if I go back to the same example, so here you see I start here and then I start doing pruning, the reduce error pruning. So you see the validation performance actually continues to improve as I prune, okay, up to some point, then it starts to decrease, right? So I could go all the way to the improvement and just stop there. Okay, is that clear? So now let's talk about rule post pruning. Rule post pruning, right? So let's take a running example. Let's say, yay, I have a bunch of tests. It doesn't matter what they are. Okay. And by the end of the test, well, every test is, let's say, binary 0, 1 kind of test. And by the end of the test, you have yes or no answers. Okay. Some decision tree. Okay. So it doesn't matter what the tests are. So the idea of rule post pruning is to actually consider every possible path and come up with rules for that path. Okay, so for example, the first path says, oh, if A is 0 and B is 0 and D is 0, then the answer is yes. Okay, then you have the second path So the second path is this one. So this is basically A is 0, B is 0, but D is 1, then you get answer of no. You can do the third path. The third path is A is 0, B is 1, then E is 0, then you get yes. You get the idea? Like so you can actually construct all possible rules, right? So once you have all possible rules, now you can start doing pruning. Like so you can say, oh, I'll take the first rule. What if I don't consider D? If it improves the validation performance, I'm going to remove the D from the first rule. The benefit of this kind of pruning is I can actually remove A. With the previous method, if I remove A, everything is gone. But with this method, I can remove A and still have the rules for classification. Is that clear? Any question? Yeah. You can, no, this is very flexible. Like you can actually remove it from one side and you can just keep the rest. Any question? Just give me 1 second. Yeah. Oh, okay, that's a good question. So like when I switch from, just give me 1 second. So when I switch from the tree to rule-based classification, right? So we kind of lost one of this nice property of the tree, which is inference is easy, right? Like with tree, the inference is easy in the sense you just follow the path, you get the answer, right? Now with rules, can someone tell me how you would use the set of rules to come up with a prediction? So given a new example, we know how to use a tree, right? How would you use a rule set? Yeah. Yeah. So you go through all the rules. Well, you're kind of losing some flexibility here because you need to go through all the rules and maybe take an average of the predictions, right? Like some rules are going to be applicable, some are not, right? So whatever is applicable, like so you take an average of the prediction. Is that clear? Okay. So I think this concludes our discussion on decision trees. Now there are a lot of nice advantages of using decision trees. Okay. First of all, they are very inexpensive to construct. So easy to implement. There are extremely fast implementations of trees that are available. Okay. And they are also very fast in inference. They are extremely fast in inference because all you have to do is like follow the tree, right? So they are extremely fast at classifying unknown records. Okay. And they're also easy to interpret. But this is true only for small trees. If the tree has 1,000 nodes, of course you cannot interpret it, right? So if you have a small enough tree, you can easily interpret. And interpretability is an important criteria in a lot of applications, like where people want to trust the system. Okay. And one of the nice features of trees that doesn't exist in other ML methods that we have seen so far is they can actually natively handle all types of attributes easily. Okay. For all the other machine learning algorithms we have seen so far, you need to convert the features, all of the features into real valued features, right? Like so you don't need to do that for decision trees. Like you can just feed in any type of feature and decision tree works out of the box. Okay, which is why decision tree and variants of decision trees are extremely popular with tabular data. Okay, so when you have a table structured data, right, like which is the kind of data you have in a lot of practical applications, right, like patient records or like the banking records, right? Like, so whenever you have records which has like a bunch of features which includes categorical, ordinal, and continual features, right? Like, so it like decision trees, and we're going to see some variants of decision trees next week. Okay, so decision trees and their variants are much more popular in these kind of settings. Like, while you have things like images or text or like more unstructured data, right? Like, so that is when other machine learning methods shine. Like, but when you have really structured data, some variant of decision tree is going to be a tough competitor for every other machine learning algorithms, including neural networks. Is that clear? Any questions so far? Okay, I think we can stop here, and good luck with your midterm preparation. I'll see you all tomorrow. Thank you.
My boss is